By this point in the series, there may be multiple computational questions that you may have. For example, concerning linear independence, you may ask if you have some vectors, say these v1, v2, v3 vectors in R3, you may ask, are these vectors linearly independent? Yet another question that you may ask is that if I give you some other vectors, say v prime equals to 10, 1, 4, again in R3, then is this in the span of v1, v2, and v3? And I think these are pretty natural questions that we probably want to address. So how do we do so? Well, at least for linear independence, the question lies in whether we can scale v1, v2, and v3 by x1, x2, and x3 respectively, add them up, and we can get a 0, 0, 0, such that at least one of the scalars is non-zero. If that's the case, then it's linearly dependent, and if that's not the case, it's going to be linearly independent. And one thing to realize here is that this is really a system of linear equations. What I mean by this is if you look at the first row, say, we have 7 times x1 minus 3 times x3 plus 3 times x3 is 0. And you can do something similar for the second and third row, and we get something like this. So the linear independence question really comes down to asking whether the system of linear equations has a solution that's not just 0, 0, 0. What about span? Well, for span, rather than having 0, 0, 0, now we're asking whether we can get 10, 1, 4. So this particular question really comes down to asking whether there is a solution to the system of equations where we're just having 10, 1, and 4. But there are many other questions that we can ask. For example, if you consider the matrix A given by these entries, and if you're considering this matrix as a linear map, so this is a linear map from R3 to R3, where we're writing this with respect to the standard basis vectors. So once again, this is a linear map that sends E1 to the vector 7, 5, 2, and so on. One question you may have is, what's the kernel? What's the kernel of this matrix? So just in case you've forgotten, kernel of A are all the vectors x1, x2, x3 in the domain, such that when we apply matrix to that vector, we get the 0 vector. And now realize, because E1 is being sent to 7, 5, 2, under this map given by A, and E2 is being sent to this column, and E3 is being sent to this column, if we apply x1, x2, x3 to that, this entire quantity is exactly going to be the quantity that we wrote down here. And of course, we again want it to equal 0, 0, 0. So the question of finding kernel of A is really the same question as analyzing the linear independence or dependence of the column vectors. Another similar question that you can ask is whether a vector, say 10, 1, 4, once again, belongs to the image of A. So the image of A, once again, is the set of all the vectors that we can get by applying A to a vector. And of course, this is exactly the same question as the one we asked for the span above. So we're really asking whether we can get 10, 1, 4 by applying the matrix to x1, x2, x3. Since we're talking about kernel and image, let me quickly mention that in the context of matrix theory, you're often going to hear kernel of A being expressed as null space of A, and image of A often being expressed as column space of A. And the term column space of A, of course, makes sense because if you look at all the vectors in the image of A, these are exactly in the span of the columns of A. Here I want to add 2 more questions. The first one asking whether A is injective. And remember that injective means that if you have 2 different vectors, then A is going to send them to different outputs. So if AV happen to equal AV prime, then we must have had V and V prime to be the same to begin with. And you may ask, how is system of linear equations going to help us resolve this injectivity question? Well, something that you can realize is that if a matrix or the linear map given by the matrix is not injective, such that we have V and V prime not equal to each other, but AV is equal to AV prime, then this is exactly telling us that A applied to the vector V minus V prime is going to be the 0 vector. And since V and V prime are not the same, we know this thing is a non-zero vector. So what this is telling us is that dimension of kernel of A is strictly positive. You have more than just the 0 vector in the kernel. And of course, the converse is true. If dimension of kernel of A happens to be positive, so you have a non-zero vector in the kernel, then A cannot be injective. So what this is telling us is that the question of injectivity is really the question of checking whether dimensional kernel of A is 0 or not, which we of course should be able to do if we can compute kernel of A. Okay, so a trick question that naturally follows the injectivity question is the question of surjectivity. Remember that a map is surjective if we can get every vector in the codomain. So if we can get every vector in R3 via this map, then the map is surjective. But how do we check something like this? In fact, we can ask a more general question than just surjectivity. We can ask the question about what is the rank of A. And rank is a term that denotes the dimension of the image of A, which can be visualized as follows. For example, if you have a matrix 1, negative 1, 2, 1, then here we visually have a two-dimensional output, so here rank of A is going to be 2. Whereas for this matrix, say 4, 2, 2, 1, we have a one-dimensional output, so we have E1 being sent to 4, 2, whereas E2 is being sent to 2, 1. And since these are linearly dependent, we're getting this one-dimensional output, and here rank of A is just 1. And in the most extreme case, perhaps, we can have the zero matrix, in which case every vector is going to be sent to 0. So here rank of A is clearly 0. Okay, hopefully this is illuminating, but the question remains, how do we actually find the rank of a matrix? For example, how do you find the rank of A? Well, this one is not as obvious, but we will be able to answer this question by the end of this video as well. Okay, but before we move on, let me quickly add 2 additional remarks. First, if you want to find, say, surjectivity of A, in this case, we just want to check whether rank of A is equal to 3. So if we can compute rank, then we should be able to check whether a matrix is surjective. But another thing I want to add here is a remark about what happens if A is injective and surjective. So if A is bijective, then we know. So if we have a matrix A and it's really representing this linear map phi, then it should be the case that phi has an inverse because A is bijective. So we have some phi inverse map such that when we compose them, we get the identity map. So here, just to be clear, let's say phi is just going from a finite dimensional vector space to itself. So here by the identity map, I'm just talking about the identity map on V, which is a map from V to V that simply sends a vector to itself. So this is exactly what the inverse is going to do. And of course, the other way should be true as well. Phi inverse composed with phi should be the identity map. And in terms of matrix multiplication, this exactly says that we should have a matrix A inverse such that when we multiply A with A inverse or A inverse with A, then we should get this identity matrix. An identity matrix, of course, looks like 1, 0, 0, 0, 1, 0, 0, 0, 1 if it's a three-dimensional space, because we want each of the basis vectors. So if I write this with respect to the basis vectors, you want V1 to be sent to V1, V2 to be sent to V2, and V3 to be sent to V3. And when something like this happens, you say that the matrix A is invertible. So the invertibility of a matrix exactly parallels the notion of vector space isomorphism for linear maps. And the technique of row reduction that we are about to talk about is going to help us resolve this invertibility problem as well. Anyway, I hope that long introduction have convinced you that we really want to be able to solve systems of linear equations. So let's take an example. Here we have a matrix, but you can also think of this as a system of linear equations. What I mean by this is if you correspond the first column with x1, then the next one is x2, and so on, such that these ones correspond to x1, x2, x3, x4, x5, then you can think about the first row of this matrix as 2 times x1 plus 10 times x2 plus 8 times x3 and so on being equal to 10. So you can think of the first row as being the first equation in the system and the second row as being the second equation and so on. Okay, so how do we find the set of solutions to this system? Well, honestly, that looks pretty hard to do. So let us first start by considering a simpler system. So let's say we have this matrix instead. So once again, we have our variables x1, x2, x3, x4, x5. And this one looks a lot easier to do. And part of the reason that it's easy to do is because this matrix is in reduced row echelon form. Which means the following things. First, if you have a row which contains even just one non-zero entry, so for example this row contains many non-zero entries, or as well as this row, as well as this row, in the case you have to have what's called a leading one. So leading one is what leads the row at the start. So here we see that each of the rows that have at least one non-zero entry has a leading one. And the second important property is that if you have a leading one, so that this is a leading one, then everything to the left of the leading one should be zeros, and everything in the column containing leading 1 should be zeros. So to the west, north, and south, we should have zeros with respect to the leading 1, and we see that right here. For example, this is a leading 1, and we see that up, down, and left, we only have zeros. And the final property that we want our matrix to have, if it's in reduced row echelon form, is that if you have a 0 row, then it should be at the bottom. Okay, so hopefully you're convinced that this matrix is indeed in reduced row echelon form, and now let's ask the question, how do you find solutions to this matrix? Well, for that there's one terminology I want to introduce. If your variable is in the column corresponding to the leading 1, so x1, x3, and x4 here, you say those variables are pivot variables. So here pivots are x1, x3, and x4. But if that's not the case, you say that the variable is free. So here free variables are x2 and x5. Given this, we find the solution to the system as follows. We first write down the pivot variables, so x1, x3, and x4, and we essentially rewrite the corresponding rows of the pivot variables. So for example, x1, if you look here, x1 plus 5 times x2 minus 5 times x5 is equal to minus 22. So that exactly means that x1 is equal to minus 22 minus 5 times x2 plus 5 times x5. And similarly, x3 is going to be 7 minus 2 times x5, and x4 is going to be minus 1 minus 5 times x5. Hopefully it's not too hard to see that this is exactly the same as the information represented here, and since x2 and x5 don't have any dependencies, they are essentially free. We can freely assign them any value. So here, let's say we're in the system of real equations, we can really let x2 and x5 be any real number, and x1, x3, x4 are now determined. So there you go. This is how you find the solution. Let me add 2 remarks here. Rather than having a 0 here, if you had, say, 1, so in this case, for this to be reduced row echelon form, we would have to have zeros above 1 as well. But if you had an equation like this instead, then this means we have to have 0 times x1 plus 0 times x2 plus 0 times x3 and so on, plus 0 times x5 to equal 1. And of course, this is not possible. So if we had an equation like this, then the answer, instead of this, would have been no solution. So that's something to keep in mind. And if our reduced row echelon form looked like this, such that every variable is a pivot variable, so here x1, x2, and x3 are all pivots, then we have exactly one solution. So here we have x1 is equal to minus 22, x2 is equal to 7, and x3 is equal to minus 1. So depending on reduced row echelon form, it's also possible for us to have exactly one solution, and it's also possible for us to have no solutions. Now, one thing I want to point out here is that there is a pretty intimate connection between the free variables and the kernel of the matrix. To see this, let's say this part of our matrix, so other than the final row, is our matrix A, and let's say we're analyzing what is the kernel of A. So for kernel of A, we're really asking for x1, x2, x3, x4, x5, such that we have zeros here. In other words, we have zeros here. And it shouldn't be too hard to see that we have a vector in the kernel if and only if it's exactly of this form. So I'm simply rewriting these equations. So for example, x1 should be minus 5 x2 plus 5 times x5. And something like 1 times x2 plus 0 times x5 is really coming from the trivial equation that x2 should equal x2, and so on. And it shouldn't be too hard to see that these vectors are in fact linearly independent simply because you have 1, 0 here and you have 0, 1 here. So that's really telling us that for each free variable, we increment the dimension of the kernel by 1. So here, for example, we see that dimension of the kernel is exactly 2. Okay, it's time to ask the obvious question. How do we actually get to reduced row echelon form? Well, to do so, we're going to use what's called elementary row operations. And there are 3 things that we are going to do. The first one is we can scale a row by a non-zero scalar. The second thing we can do is we can add a scalar multiple of one row to another row. And the final thing we can do is we can switch 2 rows. And something that you should realize about these elementary row operations is that these are reversible, meaning that we can always go backwards. If you're scaling by, say, 2, you can scale by 1/2 to go backwards. If you're adding 2 times a row to another row, you can add minus 2 times that row to go backwards, to reverse the process. If you're switching 2 rows, just switching them back is going to reverse it. So since each one of these are reversible operations, if you're applying elementary row operation, it's not going to change the solutions. So the solutions x1, x2, x3, x4, x5 is not going to be affected when we apply elementary row operations. So with that out of the way, let's think about how to actually change this to reduced row echelon form. The first thing we're going to do is we're going to start with the first column. And let's look at the first entry. And we see that it's non-zero. And if it's non-zero, what we're going to do is we're going to make it into a leading one. And to do so, we can use the very first elementary row operation. We can scale the first row by 1/2 to get the leading one. So there you go. I scaled the first row by 1/2. Now the next thing you want to do is we're still on the first column. We want to make sure that below the leading one, we have zeros. And we can guarantee that by now using the second elementary row operations. Namely, we can multiply the first row by -1, by -1, and add it to the second row to make this into a 0. And if we multiply the first row by -6 and add it to the third row, that's going to make this into a 0. And the same for the final row. So let's do so. So there you go, we have all zeros. And now we're done, for now, with the first column and the first row. So now what we do is we move on to the second column and the second row. So now we only care about this matrix. And looking at the second column, it's 0 for every single one. So we're not going to get a leading one here. So we move on to the third column. So looking at the third column, we see that here we have a 0, but here we have a non-zero entry. And since we want to ensure that each leading one lies to the right of the leading one above, we want to have a non-zero entry here if possible. So here now we're going to use the third elementary row operation of switching two rows. So what we're going to do, we're simply going to switch rows such that these two rows go up 1 and this row now becomes the final row. So let's do so. And now we're still on the third column. We want to make sure below leading one we have zeros. We're not going to care about above leading ones for now. We just care about entries below it. We are simply going to multiply this row by -4 and add it to this row to make this into a 0. So let's do so. Okay, now we move on to column 4. We in fact already have a leading one and we just want to make everything below it 0. And we can simply add the third row to the fourth row to make this into a 0. In fact, this makes everything into zeros. Now to finish, we want to make sure that above leading ones, we have zeros as well. And to do so, we can just use the second elementary row operation again. And how we can do that is by taking this row, multiply it by 5, and add it to this row to get rid of this -5 and turn that into a 0. And we can similarly multiply this row by -1 and add it to the first row to turn this into a 0. And after you do so, we can take this row, multiply it by -4, and add it to the row above to make this into a 0. So if you do all of those, now we are going to be in reduced row echelon form. There you go. And of course, it's not by coincidence that this is the matrix that we started with. Now we would be done if not for one question of how do you find the rank of a matrix? Where let us let this part be our matrix A. So I got rid of the final columns, and let's try to answer this question of how do you find the rank. But before we do so, let us try to make one nice observation. Let's say we have a matrix where we have the first column, second column, and a column that linearly depends on the first two. If you multiply the first column by 5 and multiply the second column by 2, add them up, we get the final column. And let's say we apply elementary row operation of, say, multiplying the first row by 3 and adding it to the second row. If we do so, we get a matrix like this. And now realize that if we multiply the first column by 5 and multiply the second column by 2 and add them up, we still get the final column. This is of course trivial for the first entry. To see for the second entry, realize that 5 times 3a plus b plus 2 times 3c plus d is, just by distributive properties, 3 times 5a plus 2c plus 5b plus 2d. And this is exactly what we have here. And you can make a similar observation for other elementary row operations. And what this is telling us is a remarkable fact that columns that are linearly dependent are going to stay linearly dependent. And since everything is reversible, columns that are linearly independent is going to stay linearly independent. So what that's telling us is that to find the rank of A, we can just find the rank of this matrix. And the rank of this one is very easy to find because each column with a free variable is going to depend on the columns before it. Here, for example, we see that the second column linearly depends on the first, and the final column linearly depends on this and this columns. And of course, it's clear that if you have a leading one, these columns are linearly independent. So we have found a way of finding rank. The rank is just going to be 3. But now you may have realized something. So for each of the free variable, we are incrementing the dimension of the kernel by 1. Whereas for each of the leading ones, we're now incrementing the rank of A, which is the dimension of image of A. And what do they add up to? And this is an amazing observation that this just adds up to the dimension of the domain. So here, if this matrix is a linear map, then we're going from R5 to R4. And we see that this exactly adds up to the dimension of the domain, which is 5 here. Or in general, if A is a matrix going from a finite dimensional vector space V to finite dimensional vector space W, then dimension of image and dimension of kernel adds up to dimension of the domain. And this is a remarkable effect, and it's usually called the rank nullity theorem. We're going to see rank nullity many more times throughout the series, but for now, this is a good way of ending this episode.